important. I accepted the recording.
Okay.
Okay.
So good afternoon, everybody. So you're welcome again to the lecture series. Professor Anna Sanpera will be taking us the second lecture for this series. Thank you.
Thank you. And now it says that the screen sharing is paused. So you see my screen. Yeah. Okay. So I just want to review what we were doing in order to understand how is this quantum mechanics, how we are going to treat it. So on the most important things, because I was talking quite a lot the other day. So what is important is to think that this quantum states, okay, it's a mathematical object. Okay? It's not a physical object. Okay? We have a hidden space, and this is a mathematical object which has to describe the outcomes of any experiment. Okay, so if this describes, this is a good object. Okay, so this is how we understand it. And then we say that we can understand quantum mechanics very simple, saying that isolated, I didn't say the other day, but then we saw the postulates, isolated quantum states are vectors, transformations are operators, and measurements are operators. And this is everything that we have. There is nothing else in quantum mechanics. Okay, in quantum mechanics, we have quantum states. It's not trivial, the theory, but there is nothing else. So, and then this is the just to see it. Okay, so how we saw it, we say that associated to any isolate, and this is very important. So we can only talk about vectors if we state is isolated. If not, we will talk about operators, which are density matrices. Okay? Which is we say that to any isolated physical system, and this is physics, physical system, there is a Hilbert space, and the system is completely described by a mathematical object, which is the state vector, which is a unit vector in this distance space. Okay, and this is the first postulate. And then we say that the second postulate that we saw with the other day, and we were only worried on the postulates that we needed, is that each observable, so that means each physical property of my quantums of my physical system, each physical property of my physical system, okay, is obtained. I'm mute. Okay, so let's see. Okay, so we have this second postulate, okay, which is these special operators, which are self-adjoint. And we have the third postulate, this is what we saw the other day, that measurements are described by any collection of operators. Sorry? It's complicated. Share. I thought I was sharing. Share. Now I'm sharing, I'm open, except that this is not the file that I want to share. The file that I want to share. Share. It's enough, but I was not connected here, it was connected to here. That's the reason that I had a problem. Now it's connected to the thing. That's it. Because the thing now should work, everything. So on the third postulate, we were saying that it's measurement collection of operators, which are positive operators, which they have to give and measure an output, okay, an outcome of the measurement, this small m. And we know that if the system was in the pure state psi, then we can look at the probability. So quantum mechanics is always probabilistic. Okay, and we see that the probability Pn is given by the expectation value of m/m. So that means this has to be a positive number. Okay, and the sum of all these Pn's has to be equal to 1. That's the reason that the sum of all the operators m daga m has to be equal to 1. Just summing probabilities, we have to have the unity. And if the state is pure and we have these measurements, which are PLA projectors, okay, then we know that the state after that is given by the post-measurement state psi of m, which is projecting by state psi, and then normalized. And remember that I was talking about two kinds of measurements, POVMs, the positive observable measurements. In POVMs, which is the most general measure that we can do in quantum mechanics, we don't know which is the state after the measurement. Okay, we can only get the outcome. This is important. So if we want to know which state it's after, we don't know. Okay? Well, we cannot do it that because a priori what I say is POVM, we can think that it's the measurement that we do, a projective measurement in a bigger space. Okay. So when we do that, we don't have access to the state, how it was after. We have access to the outcome, but not to the state. Okay? But this is the most, sometimes yes, no, in circumstances, because everything is a POVM. So a projective measurement is also POVM, but the generic POVM means that we will not have access. Okay? And then what we saw is that what we are going to use here is that the qubit. Okay, so we say that a qubit is the most simple quantum system, but this is the one that we are going to use in everything, almost in everything. Pure state, we say that we can write it as a superposition of the elements of the basis, which is 0 and 1. So a qubit will be always written like that, with alpha and beta, which are complex numbers. And since we say that it has to be normalized, because this is the length, and we want to give the length. So we know that the square of alpha, modulus square of alpha plus modulus square of beta is equal to 1. And since the phases, they don't matter, we normally parameterize this instead of with two parameters, alpha and beta. So take into account alpha and beta are two complex. Because here says that your screen has been paused. But why it says this? Well, yes. Okay. I wish if I can. Whoops. That was a little bit radical. This is because it's again going out of the let's go again. Yeah. Okay, let's see. Sharing. Okay, so let's see. Okay, let's see how much we found because I have not so much in the telephone either. So since these are so alpha and beta are complex numbers. So there is 4 complex numbers. Okay, so 4 real numbers, 2 complex real numbers, and now we can take one out because that's write it. Okay, cosine of theta, sine of these 3 real numbers. So this is a normal way, but how long it was. So we can write it like that. So I say that we can put any qubit. Normally we will write it in this way: psi is cosinus of theta plus sinus of theta 1. So this, okay, it's how we represent a qubit. So we take a sphere, it's called the block sphere. Okay, and now we write any pure state. It's in the surface of this sphere of radius 1. Okay. So on the north pole, we have the 0, the qubit 0. On the south pole, we have the qubit 1. And now any possible superposition, okay, we can write it of 0 and 1 in this way. And we can write it as a vector, okay, which goes from the center of the sphere to the surface. Okay, so this is cosinus of theta, sinus of theta e to the I5. Okay. So each point in the surface of the block sphere is a quantum pure state. And now, if we want to go to one point to another, we have to do a unitary. Okay? This is what we say, transforming a state. So we have our state here, and we want to go from 0 to 1. This is a unitary operation, okay, which has this form. And one has to be careful because there is a theta, and in the unitary is a theta and a half. Okay, it's always written like that. So what is important is that this only happens for qubits. So if we want to show how is a state which is not pure, is a density matrix, it will be a vector which is inside of the block sphere. And any other vector we can start and say, I start, for instance, from the 0. Okay, I apply a unitary and I go to any possible position of the block sphere. And a unitary evolution, second postulate, third, I don't know, fourth, that says that this is the evolution. Okay, so evolution has always to be done with a unitary. This is like that. I have Hamiltonian, and the Hamiltonian is e to the e times Hamiltonian is a unitary. And there is these 2 angles that we'll have to be careful. Okay, but this is a representation of a qubit. And this is very useful to think it like that. And then we saw the other day that for qubits, it's also important to have the operators that transport. So we want to have operators, transformations, and these transformations will be done by is Pauli matrices, because they are unitary. Okay, so fantastic. And on top of that, they are not Hermitian, obviously, but any Hermitian operator in this space of Hilbert space 2 can be written as a linear combination of Pauli matrices with the real numbers. So for qubits, we have everything there. And more or less, this is what we did the other day. And today I would like to finish all these bases before starting in quantum computation. So in the qubits, what we saw is what is important is that we have superposition. Okay, so a qubit can be in 0 or 1. So any superposition of 0, 1 will be a vector which is not in the poles of the Bloch sphere. If it's in the equator of the Bloch sphere, it will be equal weight of 0 and 1. Okay, and any other one would be a difference. Okay? So this is the first important thing. And the second important thing of quantum, or maybe the most significant thing of quantum, is that quantum mechanics says that the description of a whole system, which is composite, does not have to be equivalent to the description of the parts. Okay, so if you have a system which is composite, so system A and system B, okay, and now it depends. So we can say, imagine what is system A and system B. So imagine that we have a hydrogen atom, and we consider that the nucleus is system A and the electron is system B. And now we want to say, okay, can I describe a hydrogen atom if I describe perfectly the nucleus, which is for an hydrogen atom, has a proton or a neutron, so I describe perfectly that, and I describe one electron. No, quantum mechanics tell us no. Okay, so if I describe perfectly the neutron and the proton, and I describe perfectly the electron, for many things, it will not be sufficient. Okay, why? Because they are correlations. Okay, so a hydrogen atom, it's not a nucleus composed by a proton and a neutron plus another electron. It's something else. Okay, and this is important. So we have to know it. Okay, so how we are going to define this composite system, how we are going to describe it. And this is the most, one of the, I would say, the most important or the most paradigmatic thing of quantum mechanics, the one which allows us to do, so superpositions and correlations are the resources of quantum technologies. So it's like it's the petrol, all right, or it's the electricity. This is the resource. So we have to know how to describe these composite systems. And so the first thing that we have to say is we had a pure state, we have a Hilbert space. Now we have a composite system. How is the Hilbert space, okay, of this composite system? So the Hilbert space of a composite physical system is the tensorial product of its parts. Okay, so if I have a system A, which has associated a Hilbert space A, and I have a physical system B, which has associated a physical system B, the Hilbert space of the global is the tensorial product of the. And we were doing for one system, so we have to have a basis. Okay, there are many bases. We choose a basis. Now, which is the basis? Which is one good basis? Well, a basis, it's given by the tensorial product of two bases, basis of the system A and the basis of the system B. And this is how we construct that. And this is the fourth postulate of quantum mechanics. So this is an axiom. It's like that. Why? It is an axiom. Okay, it's like the first, the second, the third. This is an axiom. The state, the space state of a composite system, it's given by the tensor product of the state spaces of each of the constituents. So instead of having two, I have n. The Hilbert space will be the Hilbert space of one, tensor product of two, tensor product of three, and so on. Tensor product, it's not a product. We have to tensor. I will show you what I mean this tensor. Okay? So in the case that we have only two, which is we call it bipartite systems, and it's the things that we are going to use mostly, okay, for teleportation, for quantum cryptography. But why? Because they are simple to manipulate and because the experiments are simple. Okay, then we will talk about bipartite systems, and we will have that the orthonormal basis will be. Okay? Like I was doing before. I have an orthonormal basis for the Hilbert space H1. I have an orthonormal basis for the Hilbert space H2. And now, so in the case of the hydrogen atom, imagine that I say, okay, I'm going to describe, I will forget now about the neutron. The proton, it's one system, has a basis in which I can describe this proton. It's a physical state. I have the electron. I have another basis for the electron. And now I want to describe the electron and the proton, the product tensorial product of these two things. Okay. And how do we do it? Well, first of all, we have two tensor products, and this is what I'm saying. It's not a product, it's not a normal product. First of all, we have to see the dimensions. So if I have an electron which has dimension 2 because it's the spin, okay, and a proton which has dimension 2 because it's the spin. So the proton neutron will have a dimension 4, 2 degrees of freedom for the electron and 2 degrees of freedom from the proton. And now I have to construct this basis. And how I will construct the basis? Well, the basis I constructed like that. Okay, I take one element of the first basis and the other element of the second basis, and any possible. So you have to take into account that if I have two elements here, so two subsystems, now I have two coefficients which are different and free for each of them. Okay, so psi E1, psi E2. Okay, so the description is it's rather more complex. Okay, and how do we do it normally? Well, we do it on this tree. Okay, so I will put it here, but it's written it's the same. So it's very simple, but one has to learn how to do it. So if I have a system which is, let's say, alpha, beta, this is my system psi 1, and now I have a system psi 2. It's 1, alpha 2, beta 2. Okay, the state psi 1 times psi 2. Okay, this is alpha 1, beta 1 times alpha 2, beta 2. We do it like that. First one by the other. So alpha 1, alpha 2. I will do that. Okay, alpha 1, beta 2. Beta 1, alpha 2, beta 2, alpha 2. Okay, this is how it makes it. So it has to live in a bigger dimension, which is next, which is what it's written. And this is the orthonormal basis. Okay, and what about operators? So because we say that quantum mechanics is describing vectors and describing transformations which are done by operators. So how I create an operator? Okay, because I will do the same, because I will say, okay, I can have an operator which acts in the Hilbert space of A, which is Alice. Normally we call it A for Alice, B for Bob. I have an operator, I don't know, measuring the position of my electron, for instance. Okay, and the other one which is measuring the spin of my proton. And now I want to create something which is global. How I'm going to do it? Well, I'm going to do exactly the same. I'm going to do the following. If I have an operator B, which goes from H1 to H1, and another operator C, which goes in the second Hilbert space, is an operator, is a matrix, remember. Okay, so anything that we do in quantum mechanics is we transform vectors to vectors. This is a matrix. Okay, and now I want to have an operator which goes from the global state of Alice and Bob to the global state, so for this state, which is global. Okay. This which is global of Alice and Bob to another state which is global of Alice and Bob. Well, then I will have to multiply these operators tensorially. I will create an operator which is tensorial. And already we see that here things start to be a little different, okay? Because so this is an operator which is on my system. So my operator A here, should I read that? I should read in the following way. On my system A, okay, apply operator B. Okay, and on my system B, apply operator C. Okay, so this we have to read it like that. This is equivalent to that, if we want to understand it. Okay, A and B, when I apply it on my state side B, I can think it like A, do nothing on B, plus do nothing on A and apply B. Okay, so this is what it's saying. Apply on the first system on Alice, okay, and then apply on the first system on Bob. So we can understand it like that, these operators. And how do we create them? Well, we do the same. We multiply each matrix element by the whole matrix. Okay. So if I have a matrix which is exactly the same. So if I have a matrix for a qubit, which has, it's a two-variable matrix. A1, A2, A3, A4. Now I have to put it by another matrix, B1, B2, B3, B4. How do I do this operation? This operation is a matrix, which is the following. A1 by this matrix. So A1, B1, A1, B2, A1, B3, A1, B4. Now, the second element by all the matrix. A2, B1, A2, B2, A2, B3, A2, B4, and so on. Okay, so the tensorial product of the 2x2 matrix is a matrix 4x4. Which that's there. Okay, and now what happens? Well, this product, this tensorial product is like that because it has all the properties of the vectors, of the operators that it has. So if my operators were linear, A, it's my operator B times C, tensorial product. A will be also a linear operator. It makes everything as the operators that they are generated from. So how we have to understand, it's not so trivial this, okay? So it looks, but it's not so trivial. One has to think a little bit, okay? So what doesn't mean to have a state which is a tensorial product, okay? So for instance, one can think, but one has to be very careful that if I have, for instance, an electron, and I say, well, okay, electron, I have spin degree of freedom, but I also have position. Can I consider that position or angular momentum or spin and position, for instance? These are two different properties that they are associated to different Hilbert space, and therefore I can create, can I think that this is a composite system? But a priori, one can do it, okay? So we can use the, which is here, no? We can say that the total Hilbert space is the position Hilbert space, which is a continuum, and then we have angular momentum, which is a discrete. We could do that, okay? But it's a little bit misleading. So this is why I put here the more current way of understanding that. It's that the Hilbert space has to be associated to distinct properties, okay, or different particles, or positional energy, angular momentum, and so on. Okay? One has to be very careful on thinking of that. So, for instance, is it good to associate position and momentum? Position and momentum, it's very complicated to say that these are two things, because position and momentum, they are two properties that they do not commute. Okay, we know. So therefore, we will not associate with Hilbert space or something like that. I wouldn't do it. Okay, so one has to think a little bit about that. Okay. And now we can say, okay, we know about the systems and the way to write it, because it's very tedious to write I1 times I2 or on the operators. We don't write it like that. We write it directly in this sketch notation, in this direct sketch notation. And now we have to say which kind of a stage we have there. Okay, and here the things is when they start to be interesting. So if I have n different systems, a composite system, and I want to say which is the quantum state which is associated to the composite system. Okay, so the Hilbert space, I say it's a tensorial product of the Hilbert spaces. So the state psi, okay, we will say that it's a product state if it's a tensorial product of the elements of the space. Okay? So if I have my state, which is describing the whole system, and I can say, okay, my state psi AB, imagine it's bipartite, it's the tensorial product of my state on A and my state and times my psi on B. Okay, if this is the case, then describing the whole system A and B is the same as describing A and describing B. If this is the case. Okay? So I say it again, so I can have two systems that, for instance, they don't talk to each other, and I consider that this is my composite system. And I say, okay, I'm going to describe these two electrons that they are very far away, so they are not column propulsion between them, And one I have prepared it with a stem garlic, which has the spin pointing up, and another one has the spin pointing down, and they are isolated. They don't see each other. And I want to describe it like if it was a composite system. Well, this composite system will be the first spin, it's up, and the second down. That's fine. Okay. And it's okay, because if I describe the whole system, will be like describing one part, the one which is up with the one which is down. Okay, so this is what it would be classically, what we expected. Okay. So for instance, okay, let's see in this dimension 2. Okay. So we have this collection of states. The first one, which is superposition of 0, 0, plus, so imagine that 0 and 1 are the spins. And now I have a superposition. I have 2 particles of the spin 1/2, okay, which are in a linear superposition of being both of them up, up, 0, 0, plus one up and the other one down, plus one down and the other up, plus down, down. Okay. And I ask myself, is this a product state? And because I work on that, I say, yes, this is a product state. Okay. Why? Because if we look at this expression, we can put it like, we can factorize. Okay. And this state is like that. This expression is the expression 1. I can write it like that. This is psi, okay, 1/2. And now I write. The first spin of the subsystem A is in 0, okay, and the second one is in a superposition of 0 and 1. Plus the first spin is up 1 plus a superposition of the second spin of 4. Okay. And this is like a product. This is a product state. Okay. So I'm defining this a superposition of these two states. Okay. The second is the same because I take 0 out. This is the first case. The second case, I have 0 out times 1 square root of A of 0 plus square root of 2 over 1. So what it's telling me is I have the first spin, it's up, and the second, it's in my block sphere in a superposition of 0 over 1. Okay. So it's like that. Okay, it's more, because this is bigger, it's more pointing to 2. So this is my first spin, it's like that, and this one, so I write it in the block sphere if you want. Okay, so the first one is 0, and the second one, 2 is bigger than that will be here. Okay, and that's it. This is a good description. The third, the same. There are phases, but it's the same. I can separate it 0, okay, and 1, so it's a superposition. It's like the first one. But now if we look at the 4, okay, so any product state, this is what I say. Also, if I have a product state, and this is very important. I'm saying that if I have a product state of 2 states of P, A, B, and it's a product state, this I can write it, okay, as a state of Alice times a state of Bob. This will be a product state. Okay, so the first one, I can write it like Alice is in 0 plus 1. This is Alice. And Bob is in 0 plus 1. This is Bob. Okay, so this is, I sum these 2. So this is exactly this expression. Something which belongs to Alice. Alice is in a superposition of 0 and 1, and Bob is in a superposition of 0 and 1. That's fine, this is a product. But now let's look at the 4. So the fourth I ask, can I write this state as alpha times 0 of Alice plus beta times 1 of Alice? Vectorial product with something of Bob, alpha tilde 0 of Bob plus beta tilde 1 of Bob. So I'm asking myself, is it possible to do that for any alpha, alpha prime, and so on? No, it's impossible. Okay, it's impossible. You can try it, you can play it, it's impossible. Okay, so what does it mean? Well, it means that this state State 4, it's entangled. There are correlations. So if I try to describe, so this is a superposition, how would we have to understand that? Well, this is a superposition of both spins of my two electrons, one from Alice, one from Bob. They are up, and they are down. Okay, they are superposition of both of them. And this is has nothing to do with that one is in a superposition of their own one, which is the first case, and the second is in a superposition of their own one. It's completely different. Okay? So, and this is very important. Thank you. Okay, so in general, yes. What we will do, okay, we will say that as a quantum state, a pure quantum state is entangled if I cannot write it as a product vector. And this is, so we know so little about this, that this is like, you want to describe, you know what it's an apple, okay? And now I give you another food. I say describe, and you say it's not an apple, okay? And with entanglement, we always do the same. We know what it's a product state. We know how to describe something which I can describe Alice and Bob separately, and this is a description. And we say state, a quantum state, it's entangled if it's not like that. Okay? So we don't know how to describe it. You see what it means that? So this is the way that we have. Okay, and this is for a pure state. Okay, but when we talk about something much more general, like a mixed state, which is a density matrix, then we don't know which ones. In general, we don't know if a state is entangled or not. We don't know how to work with it. Okay, we don't have criteria. We don't understand it. Honestly speaking, we don't understand it. So it's like that. For a pure state, you factorize and you have conditions. Okay, so because it can be also very easy to factorize if you have to check. Imagine that you want to factorize two states that they are not qubits. Qubits is very easy, that they have dimension d times dimension d prime. Okay. So you have a lot of parameters, and then I will show you if you can do it. There is something called Schmidt decomposition you can do. But if I give you a density matrix, so I can do the same. Physics normally is with density matrix. I will have a density matrix that describes a composite system. And I will say, okay, this density matrix is separable. Okay, if I can write it like that. I'll show you what it means. Okay, it's very easy to understand like that. Okay. What does it mean that when we read something like that? You have to read it like that. Okay? So imagine that you have an oracle, okay, which says, oh God, whatever it says, with probability pi, and these pi's are all of them positive, are probabilities, and the sum is equal to 1. Okay, so this is like an oracle who says, with probability P1, you have to practice. Alice, you prepare your state in row A, and Bob in row A. With probability P2, you prepare the state Alice in row A2 and Bob in row A2. With probability P3 and so on. This is the equivalent thing to say that the pure state, this is the product state. This is the same for mixed states. Okay, this is equivalent. But here we know very well to see if the state is separable or it's entangled. While here, if I give you a density matrix, how is a density matrix that is entangled? A density matrix that is entangled will be like that. Okay? Equivalence, we need to do something like that. So this is, we call it separable. And I will say that rho prime of AB is entangled if cannot be written in this form. So if I cannot write it like you have done something with the same probability, I give you the probability, you prepare your state in this way, and you prepare the state in this way. Plus, with another probability, you prepare it like that, you prepare it like that, and so on and so forth. If you cannot write it like that, the state is entangled. And in general, say if a density matrix, you cannot write it like that, it's a problem that we will see in the next week. It's empty hat, which means all practical purposes cannot be solved. Cannot solve it now. We will not be able to solve it with a quantum computer. It's a problem which a priori cannot be solved. Only in some cases we know the solution, and we will see why these problems are empty hat. Okay, so which is kind of interesting that we cannot even solve this kind of thing. And now we want to see something which is different, okay? Because I say, okay, we have operators. We know that how are the operators in this composite system, but now we have something that we didn't have before, which are local and non-local operators. Okay. So what means a local operator? So imagine that I have a Hilbert space, which is a composite system. So tensorial product of n states, each of them which are Hilbert space HA. And now I say I have a unitary. So I want to see the evolution, for instance, of my state. Okay, which goes from the big Hilbert space to a big Hilbert space. And now I will say that this is local. It's local if I can decompose my unitary, which is a big matrix, okay, as the product of matrices UI, where UI is a unitary for each subsystem. Okay, so let's think it into systems because it's the best way. I have Alice and Bob, and I'll have a unitary evolution of Alice and Bob. That unitary evolution will be local if it's equivalent that Alice has its evolution and Bob has its evolution. Okay, so for instance, evolution equating the spin 1/2 is we rotated in the block sphere. Okay, the block vector, which is the spin of the atom or whatever. So if I have a local, means that my system, okay, I locally apply one operation here, and to the second system another operation. Okay. And when I have these operations which are local, and this is what I wanted to say, how do I have to understand it? Okay, so I have to understand it that when I apply a unitary operation U1 in my system 1, and in the system 2, I do nothing. Okay? Plus, I do an operation in my system 2, and in the 1, I do nothing. This needs to be local. But not all the operations are local. So obviously, if I cannot write it like that, this operation is not local. Okay, so again, imagine that I have two qubits. A qubit has dimension 2. The other qubit has dimension 2. The total Hilbert space is dimension 4. Any operator that acts in the total Hilbert space will be a matrix of dimension 4 by 4. And now, if it's local, I will say how many matrices, which are 4 by 4, I can write it, okay? I can write it as the product of matrices 2 by 2, but not all of them, obviously. Okay? So all tensorial products of matrix 2 by 2 gives me a matrix 4 by 4, but not all the matrices 4 by 4 can be written as a product of the matrices 2 by 2, as the tensorial product of the matrix 2. Okay? So I can have local unitaries and non-local unitaries. And I have the measurements will be the same. I can do measurements which are local. Okay, so I have my system, and now I apply a measurement to, I have these two qubits, and I only look at one, and I do a measurement here. This local operator means do a measurement in my system 1 and do nothing, so the identity in the second. Okay? This is what it's a local measurement. And there are measurements which are not local. So I have my 2 electrons with 2 spins, and I want to look at both of them at the same time. Okay? This is a Bell measurement and can be done. So the physics becomes much more complex, but also much more rich because we can play with these things. Okay. So now, how do we know? Okay. So I'm going to go to a final thing, okay, and then I will come to here. So if we think how is physics? Okay, so this is according to a quantum information person, but physics is like that. And it's this drawing which are here, which is L, P, and Q, and plus. So there is a set, which is a polytope. That means it has vertices. Okay, so it means it's not like an F, so it has to be a polytope, which are local states. Okay, the world is like that. They are local states. These local states are separable states. We call it sometimes classical. Okay, because in these cases, if I have a bipartite system and I look at Alice and I look at Bob, this is equivalent to look at the whole system. Okay, this is what we call it classical separable. Okay, these sets, they are inside of something more general, which is called quantum. Okay, and these quantum states are broader, and it's not a polytope. You see here, it's something which is, it's a convex set, so it doesn't have any phase, any facet. Okay, so it has infinite borders. Okay, this is the set of quantum states, okay, in which there are states which are entangled. And this is the reason that it's like that, because they are entangled. And then above this thing, there is something which is another polytope, which is not signaling, because physics, not quantum, tells us that nothing can go faster than the speed of light. And this is how the world is, okay, and how we see it in the quantum info. So I wanted to go here. Okay, so it's a little bit to have an idea, and everything we can explain it with two systems. Of course, if we go to n systems, everything is much more complex, but there is not me. So if we go to the systems, now this is the question that you were saying, how do we know if a state is, I give you a pure state, okay? This is called the decomposition, and it's very useful because this allows us to do the following. Okay, so I give you a bipartite system, and this is only truth for bipartite system. So quantum mechanics is very complex, because if you have already three parties, we don't know anything. Okay, so if I have Alice, Bob, and Chappie, and they decided to start to play games and so on, it's very difficult to explain. But if we have two, which is normally called 1 and 2, or Alice and Bob, or H1 and H2, so I like it to call Alice and Bob. Yes, like that, because it's more graphical. Okay. And now they have a state sign which belongs to Alice. And of course, they want to know, because they want to do teleportation, they want to do quantum cryptography, they want to do quantum computation, they want to do dense coding, they want to do whatever. They need to know if this state is entangled. How can they know if it's entangled? Well, 100 years ago, it was a physicist, a mathematician, Schmidt. He didn't know about quantum mechanics before, but it shows the following: that if I have two systems of dimension D1 and D2, okay, there is a basis which is special and unique, okay, in which I can write. So normally, if I write this, I have to write it like sum, well, over C of Alice, C prime J of P, I of Alice, and J of P. Okay, where I goes to 1 D1 and J goes to 1 D2. These are the degrees of freedom of the system. But there exists a single basis in which I have only one index I. Okay, and this basis, it's called the Schmidt basis, and you can find it. It's very easy to find it mathematically. But what it's telling us? Okay, so forget about the mathematics and what is the physics that it's telling us. So this sum goes from lambda I from 1 to the minimum value between D1 and D2. So imagine that I have two spin 1/2 particles. The minimum value is 2. Okay, what is that? Because it's telling us that I have 2 degrees of freedom. How many correlations can I have? Well, I can have at most 2 degrees of freedom which are correlated, because there are not more. Imagine now I have a system with 3 levels. So spin 1. That has level 0 plus 1 minus 1, and then spin 1/2. Okay, so here D2 it's 3 and D1 is 2. How many degrees of freedom I can correlate? At maximum 2. So I only have 2 here, so I cannot correlate more. I cannot correlate 3 because system A only has 2 degrees of freedom. Okay, so this is what it's telling us, this expression, that I can always write my wave function, my pure state, okay, in this basis. And now what happens? If I have a single coefficient of this lambda, this is a product. This is what we were writing before. This is a product state. I can write that psi of AB is psi of A times C of B Okay, this is a problem. But if I write that psi of B dt is lambda 1 psi of A times C B plus lambda 2, another state of A. But this is definitely this is an unbalanced state. Okay? I cannot write that. It is not states that I cannot write. So this is exactly how it goes. For instance, if I have my state which is 0, 0, minus 1, 1. Right, that is perfect. Okay, so this is state of this plan, is of this one. This is what normally you say this is single. Okay, and have spin up, that's spin down, spin down. Okay. It's nice thing. So I have 2 electrons, and then I have that they are both of them spin up in a linear superposition of both of them spin up and both of them spin down. And of course, here is when the physics starts to be quite interesting, no? Because if we do something like that, okay, so in these entangled states, so now imagine that we want to do these measurements. So the first thing that we have to say is, imagine that I have that. So there is I'm Alice, there is a Bob there. We have prepared our state, which is in this kind of superposition. And if it's a product state and I have to describe my state, it's enough that I look at my state. This is very easy. But if I have an entangled state, I can ask, which is my state? Well, so if I have this state like that, 0, 0 plus 1, 1. So now you have to ask the following. And this is where the game starts. Imagine that I have my state, Alice and Bob. It's a superposition of 0, 0 plus 1, 1. And I say, in which state is Alice? I ask you, what is the state of Alice? So if I have my state like that, I say my state, my combined state is 0, 0. I can say it's up, spin up, which is, we are here, which is the state of Alice with mine? Spin up. Okay. And the state of up, spin up. But if I'm here, which is this combination of up, that's down, and I ask, which is the state of Alice? How is the spin that Alice has? Yeah, it doesn't have to spin the time, okay? It doesn't have to spin the time. So what does it mean it doesn't have to spin the time? It means that if now I'm going to do here, I say, okay, I want to calculate how to do it. So what I'm going to do? I'm going to do a measurement. If my spin is 0, 0, I'm going to do a measurement. So, and I'm going to measure, and what I will find? Well, I will find that I have a 0, and you are Bob, you have a 0. Okay. But we are 0, 0 plus 1, 1. I'm going to measure. Okay. And when I measure, I will find that with probability 1/2, my spin will be up. Okay. And with probability 1/2, my spin will be down. So this is the state of the end. This is Alice, this is Bob, this is Alice, this is Bob. And this is one small this probability 1. Okay. So, and this it's funny, no? Because it's telling us several things. No? So one thing is it's very strange. Yeah, it's when quantum mechanics start to be very convoluted. No? Because imagine that I have this state, no? Which is, sorry, I'm going to move because somebody. So I have this state 4. Okay, I forget about the phase. I don't care, which is 0, 0 plus 1. So I measure. I'm Alice. I measure, and I get that my state is 0 with probability 1/2. And without doing anything, I know that Bob has his spin in 0. Okay? But quantum mechanics and the world, we know nothing can be superluminal. We cannot transmit this information because that will be faster than light. Okay? So what does it mean that? It's that faster than light. You understand what I mean? So I have my state in the fourth case, which is 0, 0 plus 1, 1. I don't care about this phase, it's not important. And now I prepare measurements. Okay, so I want to know. So this is like spin up, up plus spin down, down. Okay, and this can be two systems which are very far away. So one is here at this room in Kigali, and the other one is in Barcelona in my office there. Sal is here and Bob is there. But we have prepared this state 0, 0 plus 1, 1. You can do it. Okay. And now I measure here in Kigali, and I obtain that my state is 0. Okay. So it's the first 0. So this is spin up according to this formula here, the first 0. Which is the state of the other spin, which is in Barcelona? Is 0. But how that can be? Because nothing can go faster than light. This is immediate, okay? So I'm transmitting something faster than light. No, I cannot transmit something faster than light. So where is the catch here? What I'm saying wrong? Well, the thing that I'm saying wrong is this doesn't help for anything, because now I want to repeat the experiment, okay? And before repeating the experiment, and this is super non-trivial, it's very subtle. So I don't believe that any of you will understand it, because you have to think a little bit about that, okay? But that means that if I don't do anything, can I say if I'm going to get a 0 or a 1 before I measure? So if I have my state, which is here, 0, 0 plus 1, 1, and I measure the first qubit, how do I know if I'm going to get a 0 or a 1? Can I know it? But the answer is no. I cannot know. I can only know that with probability 1/2, I will get a 0. And with probability 1/2, I will get a 1. So if I repeat the experiment in identical conditions 1,000 times, the only thing that I can say is that 500, on average, 500 times in the order, I don't know, I will have a 0, and 500 times I will have a 1. And I can have the following. I do the experiment 0, I obtain 0, spin up. I do the experiment 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. I don't know the second. It's impossible. It's absolutely random, because this is quantum mechanics. So I can never transmit anything, because priori, okay, in order to transmit, what do I have to do? To transmit information, I have to say, okay, if I measure my spin and my spin is up, I'm going to codify this like a bit 0. Okay, I want to transmit a number. Okay, between here and Barcelona. I say, okay, we share these states which are entangled. We share 20 of these states. I want to transmit a number. So a number, how do I do it? I codify a number with zeros and ones. No, 0 is 0, 0, 1 is 1, 0, 0, so on in binary way. But to transmit this number, I want to transmit the number 13 maybe. Okay, I have to first of all to write 13 in binary. I think I don't know maybe, but I think we can do it. And then to transmit it. Well, this I can do it if I have the right sequence. So imagine that my number 13 in binary, which I don't know what it is, I have my idea. Okay. So imagine that the number 13 is a sequence which is 0 in classical 0, 1, 0. It's not this one. I want to transmit this number, and I'm using this case. Can I transmit this number from here to there? No. Why? Because the only thing that I can do is I measure and I obtain a 0. That's it. And I say that Bob has a 0. I know it because they are sharing the state 0, 0, 1, 1. I take my second state. Okay, so we are sharing these states. This is a collection of states, which are of the form 0, 0 plus 1, 1. Okay, so this is iris and this is 4. So I take the first one. I mention it's a zero. I say, well, Bob has a zero. That's it. But that's very good because I want to transmit this number. But the next one, I have no idea if I'm going to have a zero or one. It's completely random, right? So maybe I will measure a zero and I will say, oh, it has a zero. Okay. And maybe the third, I will measure a zero and it has a zero. And maybe the fourth, I will measure and it will be one, but it's completely random. So there is no way I can do that. So there is no information associated. It will be information. I will be able to transmit information faster than light if I was able to predict which is the outcome that I'm going to have. But since I cannot predict the outcome, I cannot transfer anything. Although, okay, and this is everybody speaks on their own interpretation. So many people hate this interpretation that I'm saying, and they are going to say that this is wrong, and other people has another interpretation, and I will say it's wrong. So this is a personal choice. Although I will say that when I measure zero, I know already that Bob, whatever he is, has a zero. Okay, so this is a very subtle point of quantum mechanics.
So I'm just speaking that kind of
Yeah, but this is exactly how you will do. Yes, but you don't know which 20, but you don't know which one of the 25%. Okay.
Yeah, well, right.
No, but you don't know. This is teleportation works exactly like that. Okay, so if you don't do anything, you don't do anything. Okay, you have to do identity. But if you don't do anything, 25% of the cases you will be right without even transfer anything. But you don't know, but it's the same. Teleportation you transfer to this is the same. But if you don't know which one of these 25%, it doesn't matter. If you put the data theory, say, well, 20 times, 25% of the cases I will transmit in this way. But which ones of this? So I give you a batch of 110, it is 25 good ones. You have no idea. You know that on average, 25 you have done well, but which ones you don't know. So therefore you don't transmit. This is where what happens. And this is very important, okay, because everything, but most of the things they are based on superposition, but everything which is related to security, in cryptography or communication, and so on, it's based on this factor, on the fact that they are entangled states. Okay, so exactly. So we have this state, we are discussing about this state, okay? And this is what I was saying. So I have this state, 0, 0, Alice and Bob, plus 1, 1, Alice and Bob. And now B, Bob measures in the standard basis, which is the probability. How I have to calculate, what does it mean it measures in the standard basis? Okay, when we have these things, I say I have Alice and Bob measures. Well, that Bob measures means that Alice doesn't do anything, so the identity, I write it like that. Okay, Bob measures in the 0 basis, this is the first line in yellow. That means Alice does nothing on her state, it's not measuring, so the identity operator, and Bob projects from 0, 0. And if you take this state and you create this, okay, so then you will see that this gives you 1 half, it's a probability. And in this case, what is the state after measuring? So this post measurement, what is the 0, 0? And in the case that Bob chooses to measure in the 1, 1 basis, he will also find this 1 half, and the post measurement will be 1. Okay. So what happens for Alice? And we can understand what is the state of Alice. Okay. So if Bob doesn't say anything to Alice, so Bob measures and doesn't tell me the result. How can I understand which will be my state? My state will be half of the cases a superposition of 0 and half, well, it will be in the 0, 0 plus 1, 1. Okay? It's not going to be a pure state because it's not anymore. I know everything about the state. Okay? So one can only say that Alice will be equally in the state 0 and in the state 1. Okay, so and this, it's not written here, but this is how you calculate the state after the measurement. Okay, so this is the reduced density matrix. How do I see my state after Bob has measured, or how Bob sees his state after I have measured? Or how I see my state if it's combined. If I have so this is very easy, no? So if I have a state which is means like that, I have a state, okay, which is from Alice and Bob. And now I want to say which state Bob is, okay? So the state that Bob is, I will say is the following: is I will place Alice out of this state, okay? And that will be the state that corresponds to Bob. Okay, so this is what it means. So if I have a state which is entangled, and I'm Alice, and my state is entangled with Bob, in order to see what do I have to trace out Bob. Okay, I take him out, okay, and then I will have my state. This is an operation, and you will detect. Okay, so I will finish here. I wanted to say, okay, so to summarize before I start next week with quantum computing or complexity theory, rather. So how is the world according to quantum information theory? Okay, so how do we see the world? And it's relatively easy. So we say, well, in the world there are states, which normally they are not real states, they are density matrices, which are emission operators, which are time positive, and they have this one. We have resources that we want to use for things. Okay, and resources are quantum correlations and superpositions for given. These are the resources. Like in energy, the resources are or to do work, the resource is energy. Okay. You always have resources for things, no? In our world, how it's organized, the resource is money. Okay? So if you want to buy something, you need some kind of money, whatever this money is, and if you don't have it, so this is a resource, that something that allows you to think something. So in quantum information, if you think like that, the resources are occurrences, okay, superpositions, that allows you to do a lot of things, or quantum correlation. And then what do you want? Well, you have transformations, okay, so operators which transform from a state to another. These are called quantum loops. These are the operators that we have seen. And you have measurements. You will end up doing measurements, which will be projective, UVMs. And now you have a task. Okay, so in quantum information, we have a task. Which is this task? Well, this task can be very different. So for instance, you want to know if a state is entangled or not. This is a task. You want to know if two states are equal or different. So you know that in classical physics, we can distinguish that. But in quantum mechanics, we cannot distinguish two states, okay, unless they are orthogonal. We cannot distinguish them. So I want to know with which probability I can distinguish these two states. Because I need, so somebody give me a set of states, and I want once for doing something because I haven't done the other once not. So I have to be able that when I do measurements to say, okay, this one out, I don't want it, but this one I want it. So this is discriminating states. I want to do computation. Okay, so I need probably some states, and I want to put some gates. I want to do communication. Okay, I want to transmit dates from here to the other part of the world, which I have to be sure that it's completely secure because nobody wants that learns who is my lover, for instance. Okay. So I want that to be absolutely secure and nobody can read it. So I have to use quantum entanglement. For the governments, they have these messages that they don't want to be, or the companies or whatever. Or I will need entanglement for that. I want to do simulations. This is another task. Okay, I want to understand how condensed matter works. And in order to understand how condensed matter works, I have to simulate the system, which is very complex to simulate because condensed matter is very complex because there are many parties and each party there are quantum parties, there are correlations. So there is no possibility that a classical computer will ever find the ground state of some problem. So for instance, finding the ground state of some complex problem in condensed matter, it's super difficult. So difficult that not even a quantum computer will be able. But these are the kind of things that we say, okay, not a quantum computer will be able to solve it. Can I approximate it? I want to know the ground state of a system. Can I approximate it? How well can I approximate it? I want to measure with metrology. I want to measure with the maximum precision. Why? Well, because there are things which are important. For instance, you want to measure if it's going to be a tsunami, okay, much before, for instance, Japan, okay, that there are a lot of volcanic explosion. So they have a system that in 3 seconds, they can switch off all the trains and all the power stations, central power stations, so that it didn't happen when it was tsunami 12 years ago. They were very efficient. So 3 seconds compared to 2 seconds and a half is a big, it's very important. So therefore, you would like to measure maybe if there is a wave, which is very far away, propagated by a tsunami before it arrives. Or, for instance, gravitational waves, how they were detected now, 100 years after, well, using quantum optics, using an interferometer. And so you want to have a very precise measurement, and it's a quantum measurement. You squeeze light, so it's a quantum measurement. So there is a lot of things that you can think you can do. Okay, and which is the task? So you have the task, and then which is the objective? It's to create a protocol in order that you optimize that. So how is the best thing you can do in order to achieve this? Sometimes you can do it very well, sometimes you cannot do it very well. Okay, and I think I will finish here today. And on this other week, I would like to talk only about complexity and which kind of problems we can solve with quantum. Okay, and that's it. I will leave this already. Well, how we do it, that it doesn't matter, and this is how it's the work. So the only important thing is that they are correlations, and correlations means that if I have two systems, okay, I just sum up, and one is prepared in the state X, the other one is prepared in the state Y, and then I have as an output A and B. It's correlated if I cannot write it like the product of two probabilities. That's what it means correlation. And this is how we separate the work. And that's it. I don't know if there is any question.
I have like this. The first one is nature itself. So the system,
Yeah. By minimization, but imagine that you want, so this is also, yeah, this is a minimization problem that it does. So this is true because you know that there is a principle of minimal energy, so everything works. So this is also one of thermodynamics, but and this is my personal opinion. There are many systems that it doesn't happen in nature. Okay, so like there are many materials. So if you go to the periodic table, okay, there are many of the elements of the periodic table which are artificial. We have created. So condensed matter is much richer than that. We know very little of them. Okay, but, and then in these cases in which we created, how we are going to know how it's the ground state, we don't know. Yeah, but yes, I understand what you mean, and you are completely right. But imagine that you want to do chemistry in this way and chemical reactions, and then you have to know exactly which is the energy of the steps and so on. So you will say yes, but for a chemical reaction, we are not able to know how all this process is. Or for instance, more simple, all right? So superconductivity. So superconductivity is known since many years, but nobody knows which doesn't allow us to create other states which are superconductors, and the superconductors of high temperature, which are -70 degrees Kelvin. Okay, these ones there. But if we understood and we know, and so you can say, yeah, the superconductor, it goes to the ground state and it's superconductor. Yes, but why? We have no idea.
Other questions. So
my opinion is I never have an opinion about this thing. Okay, because well, I mean, I will say, but this is, I mean, I am not a specialist, right? But in order to protect entanglement, it's so delicate that as soon as you are at room temperature, I will say that nothing is because they are, well, this is the transition from quantum to physics. So it's very difficult to have all these computers working on the phone because, I mean, it's true that not everything has to be, there are things with nitrogen vacancies, so you can do it from temper, well, not from temper, but three edge, I don't know what to say, but there are things that they work at room temp. But I don't know, it's kind of, I wouldn't say that it is, but I don't know. Well, I don't know even what it's consciousness, even classified, I don't know what it is. Yes. Very difficult. I mean, I believe that we are chemical reactions. I don't, that everything is a chemical reaction. So this is a very agnostic point of view, like me, everything is a chemical reaction. Very difficult to say. Although, I mean, I know that how we express feelings is so different. I have no idea, I have no idea that it's too complicated. I think biology is very complicated, much more complicated than quantum and philosophy of. But it's good to ask. Many people really come. The only thing that one has to be careful is to have a scientific. Sometimes you talk about people and they don't know anything about quantum. Then I don't. There are people who will. Okay, thank you.
Can I ask questions?
Oh yeah, sure.
Oh, thank you very much for the very beautiful presentation. Yeah, I am Dr. Diko Dauda from Nigeria, University of Ibadan. I am a mathematician, so I'm sorry if I have to ask some things that might be very elementary. Yeah, the first question I have. Yeah, the first question I have is this. In the case of quantum entanglement, can we look at our H as a tensor product of asymmetric and antisymmetric
Yes.
objects? So, I mean,
Yes.
when you said H is not equal to, that's how to define the quantum entanglement. That's the first question. The second question is this. In the case of quantum optics, where we apply the Mach-Zehnder objects, I mean, that's one of the applications of quantum optics. Can this expression, can we express them in simplified form as we have explained in the cases that you have shown us now with the cat and the brass? You get my question? Yeah. Okay, then thank you. Then
one I understand it, but okay. And the second one?
Yeah, the second one.
Mach-Zehnder interferometer. Yes, you can do it with cats and brass. Yes, you can put the whole quantum mechanics. So the first one is very interesting, and I like it very much because we are completely right that you can separate everything in the symmetric and anti-symmetric subspace. And let me tell you that I have been working maybe for 5 years in the symmetric subspace. So this is one of my research areas. And even that, it's very difficult. So we know that it's very related to mathematics. So it's very nice because it's very related to properties of mathematics, the symmetric subspace, with something which is called all these, I don't know if you are familiar, compositive matrices and CP maps and so on, CP matrices and so on. It's interesting, but it's NP-hard. Even in the symmetric subspace, which is a small subspace, the problem is NP-hard. So when you increase the dimensions, it's not solvable. Okay? Like it's not solvable, and we know it because we know that it's solvable in mathematics. So you do these two things. Okay? And the second one, yes, you can express anything amongst Mach-Zehnder. You can write it always in this Dirac expression of cats and so on. Absolutely. So you write your Mach-Zehnder and you say, okay, it's polarization of light. So 0 will be vertical polarization like the spin, 1 horizontal polarization, and any polarization which is a linear superposition could be this kind of circular polarization. So, but you can write it, and it's the way that we do it, which is much easier. Yeah.
Okay, so can you give some references where I can do that?
I will I will
want to
put it
also,
in the PDF.
please, okay, please,
Okay.
I want to also observe that though I've followed what you did, but if a video of your writings when you are explaining on the board can be shown, that would be very good for us who are online, because I am from the theoretical direction, so I need to see more of the ideas behind the simplification and the
Okay, I can
complication.
do something which I understand. Yeah. This is the difficult thing, to do something which is at the same time online and essential. The best thing I can do it, which I can try to do it for the next week, but I'm not very good on handwriting. This is the reason that if I have a blackboard, I'm good. These are very bad in the way. But I can try to do it on the iPad, then do a combined thing. So when I write it on the iPad and then you see it. Because I understand that. For me, it would be possible to follow it. It's only formulas and PowerPoints. I understand. But I need to see the derivations. If not, it's like for me, I'm blind to the other things. So I will try to do it. Yes.
We appreciate that. Then the videos that you have done, the last class and today's class, I hope we'll get it too.
Yes.
The videos.
Yeah, they are available. And yes. Okay.
Thank you so much. I would love to collaborate with you. Yeah.
Thank you.
Thank you.
Bye.
Yeah.